I'm Antonio Rodà, and with Professor Giovanni De Poli, we are part of the Centro di Sonologia Computazionale, that is a research laboratory of the University of Padova, founded in 1979 to support research, musical production, and education in the field of computer music. And 2 decades ago, we started being interested in the digitization and enhancement by means of digital technologies of musical cultural heritage, in particular, all analog recordings and more or less ancient musical instruments. As concerned musical instruments, traditionally, playable copies or replicas of ancient instruments are built by craftsmen. This practice allows us to play the instrument and to listen to its sounds. However, the manufacturing process is usually slow and expensive, and often one or only few copies can be built, limiting the access of the instrument. Moreover, when the reconstruction is uncertain due to lacking information, it is difficult to test and evaluate different hypotheses. To have a digital model of a musical instrument, we can start from different sources, pictures, textual descriptions, technical drawings, and of course, archaeological finds. In the latter case, we need to measure these finds by hand, maybe, or better, by using recent techniques such as structured light scanners or computational tomography. From these techniques, we can directly obtain a first rough three-dimensional model of the instrument or of the parts of the instrument. And then by means of numerical processing, we can virtually restore the instrument. Interesting, we can obtain many different versions using different sets of assumptions and hypotheses. From the restored model, then we can also obtain a simulation of the sound that could be produced by a musical instrument with such geometrical and functional properties. And the generated sounds can also be used as a validation of the hypothesis used for building the model and can sometimes suggest further modifications to the model. The three-dimensional model can also be used as a guide for a craftsman to construct physical copies of the instrument, or more easily, a physical version of the model can be directly obtained by an additive printer. Finally, the large amount of data and knowledge coming from this process can be used to design novel approaches for enhancing the access to these instruments by scholars and general public. Today, I'm gonna show you a case study concerning an ancient Roman brass instrument hosted in the Civic Museum of Berriguardo. And this is part of a really multidisciplinary project that involves musicologists, computer scientists, and engineers. And I must acknowledge all these colleagues and the current and former directors of the museum. The instrument was found in Vogenza, close to Ferrara. And in the context of the excavations of a Roman villa of imperial age, you can find more details about it in this volume. The instrument is made of a metal alloy and it is broken into 8 pieces. And each piece suffers from large holes and damages. The first rough model was acquired by a structured light system that can reach an accuracy up to 10 micrometers. The rough three-dimensional model presents several challenges because the parts are pretty damaged. There are many missing areas on it. Moreover, to reconstruct the entire instrument, we need to find a strategy to recombine the 8 pieces in a meaningful way. And for the restoration, we propose a novel methodology divided into 3 main steps that are data cleaning, part replacement, and reconstruction. All the details can be found in these publications, but now in the next, I will give you some brief explanation of these steps. The first step is data cleaning. Normally, when you scan a manufacture such as a flute or a trumpet, laser scanner returns a 3-dimensional model of the outer surface of it. In our case, damages cause the accidental scanning of some interior parts that must be removed. First, each part was cut by parallel planes, obtaining a set of elliptical sections. Then we estimated the centers of each elliptical sections, and in this way we estimated the central axis of each part by connected these centers. That is the red line that you can see in these pictures. And the central axis allow us to easily determine the areas to be cleaned. The those areas here in yellow with a normal vector pointing toward the central axis. Once we have a good approximation of the central axis of each part, we can also estimate the orientation of each part by following a plane fitting algorithm. This is the result of this algorithm. You can see the plane, the fitted plane in blue, and then we can rotate all parts in order to put all the parts on the same plane as here in this figure on the right. In this way, we reduce the alignment problem from 3 dimensions to 2 dimensions. Finally, we can align the parts by rotating each part until the axis ending of the previous part has the same direction. In mathematical terms, we can say the same derivative as the axis beginning point of the next part. The alignment was obtained by solving then a common optimization problem. And here it is the result of the alignment. In the last step, reconstruction, the major and minor axes of the elliptical sections are fitted by a quadratic function. You can see in this graph the length of the axis with points and the quadratic fitting curves in a continuous line. And finally, we reconstructed the entire instrument by using this quadratic function. You can see here on the left the reconstruction in blue and the original pieces in green. Starting from the model of the reconstructed instrument, it is possible to simulate the sounds that it could generate. These sounds can be simulated following different approaches. Roughly, we can follow an analytical approach, a numerical approach, or a combination of both of these approaches. And the Vogenza instrument has no holes, widths, or sliding parts. Therefore, the fundamental frequency of the tones that can be generated depends largely by the peaks of the acoustic impedance of the bore. From an intuitive point of view, the acoustic impedance of a vibrating body represents how easily that body can vibrate at certain frequencies. In this picture on the left, you can see an example of acoustical impedance of a bore. If we look at the peaks of this function, we can find the resonant frequencies that we can read on the horizontal axis, the resonant frequencies of the instrument. And the impedance, the acoustical impedance of the Vogensal instrument can be estimated analytically, starting from the well-known wave equation and solving it in the case of a wave propagating in a bore with an increasing diameter. We obtain, therefore, this equation, the equation 1. This equation has many parameters that can be easily calculated from the 3D model, but one that is the new parameters, that is a coefficient related to the shape of the flared part. To estimate the new coefficient, the flared part is usually approximated by a Bessel function. And then by fitting the data obtained from the reconstructed model in blue, the points in blue, by fitting this data with a parametric Bessel function, we obtained a value for the new parameters equal to 0.71. Finally, by applying the equation 1, we calculated the frequencies listed in the table that represent the first 10 tones that could be generated by our constructed model. Of course, the first 10 fundamental frequencies of these tones. Now it is time to listen to the sound of this unset instrument. I start this. You can listen now this 10 sound. You can also see in this table that the frequency ratio between two subsequent sounds, the fundamental frequency of two subsequent sounds, follow quite well the natural harmonic ratio, and quite well for the higher sounds, and with not so well for the lower sound. Models and sound simulations can be also used to enhance the access to these instruments, and digital technologies offer many possibilities for interacting with the instruments. And here you can see a couple of examples coming from previous projects. And on the left, you can see a museum fixed installation related to a pan flute, here in the picture, hosted at the Museum of Archaeological Science of the University of Padova. And we have in these pictures two modalities to interact with that instrument. The first modality is based on touch. You can see the video. The other modality is more natural because it includes a gesture, the gesture of blowing in a hole, in a certain way, reproducing the natural interaction with the instrument. And here in the middle, you find another example. In this case, we have a mobile applications, and this is related to a system. In this case, we emulated the physical movement of the keys and the sound of the impact. In conclusion, the problem of giving voice again to disappeared instrument is not only related to ancient musical instrument. Here in the right part of the slide, you can see some pictures related to the Studio di Fonologia of Milan, one of the first electronic music instrument. Here we are in the 50s, and the man in this picture is the composer Luciano Berio. This very particular instrument disappeared about 50 years ago, and we were called more or less 10 years ago to produce a digital replica of this instrument that does not more exist. This digital replica simulate the original electronic circuits starting from pictures and technical drawings. This is the project about the Roman brass instrument. Is an ongoing project. Therefore, there are many improvements. For example, the algorithm can be improved for the very damaged parts of that instrument. And then we are planning to generate different models based starting from different assumptions. And also, the equations that we used to estimate the peaks of the acoustical impedance are only an approximated solution of the wave equation in a horn-shaped board. Therefore, we are planning to explore other approaches. And the last point is, of course, the fact that the simulated sounds up to now does not consider the interaction between the player and the instrument, both for the acoustic coupling, but the real problem is how to take into account different performance techniques or different sound effects that can produce with the instrument in the interaction between the instrument and the player. Thanks for your attention.